In this video, we're going to introduce a new family of groups, which we will call the symmetric group on n elements. So first of all, suppose I have a set A. Then the symmetric group on A is the group of bijections from A to itself under function composition. That's the operation. Alright, so for example, I could say A is the set of integers, and then the symmetric group on that would be the group of bijections from the integers to the integers under function composition. But now as I say this, I realize I'm claiming something as a group, and I haven't proven it's a group. And I feel like anytime we claim something as a group, we should show that. So let's see if we can show that what we were talking about here is a group. So why is this a group? Why a group? Well, we need to check four things, as usual. We need to check that the set is closed under function composition. We need to check that the composition operation is associative. We need to check there's an identity. And we need to check that each function or each bijection has an inverse. All right. Oh, and by the way, just a bit of notation. When we talk about the symmetric group on A, we will usually call that S sub A. All right, so let's check that this is a group. First of all, why is this set closed under multiplication or under function composition? So to show that our set is closed, I'm going to let two functions be bijections from A to A. And in this course, it's going to be customary when we talk about bijections or when we're talking about elements of the symmetric group, we're going to use Greek letters like alpha and beta. So let's suppose alpha and beta from A to A are bijections. Okay, then alpha and beta are 1 to 1 and on 2. That's what it means to be a bijection. All right, so you may remember a theorem from a previous course that if alpha and beta are both 1 to 1, their composition is also 1 to 1. But I'm going to prove that here just for the sake of having a complete proof before us. So to show beta compose alpha, and I'm writing them that way because, as always, composition means that we perform the function on the right first, then the one on the left. And I feel like we should do alpha first. So to show this is 1 to 1, 1 to 1, well, let's suppose that x and y are in A such that beta compose alpha of x equals beta compose alpha of y. Then we need to show that x equals y. Okay, but given that this is true, this means by the definition of composition that beta of alpha of x, remember beta and alpha are functions, equals beta of alpha of y. And because beta is 1 to 1, this implies that alpha x equals alpha y, because beta of both of those is the same element. So this is since beta is 1 to 1. And then that implies that x equals y, since we know alpha is 1 to 1. All right, and that's what we wanted to show. So beta compose alpha is indeed 1 to 1. Great. All right, now what about showing that beta alpha is on 2? Well, let's suppose y belongs to A. I need to show that there exists some x in A, some input, some x in A, such that beta compose alpha of x is equal to y. All right, so to show that, well, that would mean that beta of alpha of x is equal to y. That's what I need to establish there. I need to find some x that would make this true. Well, the first thing I'm going to do is I'm going to show that it's possible for this to be true. I'm going to find some element of A such that beta of that element equals y. So I know since beta's on 2, there is some z in A such that beta of z is equal to y. Okay, so that's something that I could certainly do. So that if I could make alpha of x equal to z, then I think I'd be done, because that would mean then that beta of alpha of x equals beta of z, which would then be y, and that's exactly what I want. All right, well, since alpha's on 2, there is some x belonging to A such that alpha of x is equal to z. So then once I have those in place, so now I've defined z in A, I've defined x in A, and x is the thing I needed to define. So then I have beta compose alpha of x equals beta of alpha of x, which is beta of z, because that's how I defined x, and then I defined z so that beta of z would equal y. So now I have an x such that beta of alpha of that equals y. Yay. So beta compose alpha is on 2. Therefore, beta compose alpha is a bijection because we've shown it's 1-to-1 and on 2. Thus, this set, the symmetric group on A, the set of all bijections of A, is closed under composition. All right, so that's one part of the proof that this is a group. Now I need to show a few other things. I need to show that the operation is associative. I'm actually not going to do that in full detail here just because we've talked a little bit about why function composition is associative. It's really just a matter of keeping track of what happens to an element of the set as it goes through 3 functions in succession. So I'm going to call that having been done. All right, so let's mark off things that have been done here. We've got this. We've checked that it's closed. I've claimed that it's associative. You can go back and check that yourself if you want. Now let's do the fact that there is an identity in this set. All right, when we talk about an identity function, a lot of the time what we're talking about is the function from a set to itself that takes each element to itself. So the function, which I'm going to call epsilon since we're using Greek letters today, and also because epsilon it corresponds to our letter E, which is often used for a group identity. So the function epsilon from A to A defined by epsilon of x equals x for every x in A. I claim this is, that's syntax error. This is an identity not for A, for S sub A. That it acts as an identity element, which means if I compose it, either pre-compose or post-compose with any other bijection in S sub A, that I get the same function back. So we'll prove that. All right, well, suppose alpha is in S sub A. That is, alpha is a bijection. From A to A. So we want to show that epsilon compose alpha equals alpha, and also we want to show that alpha compose epsilon is alpha. We need to show both of those things are true. All right, so we're just going to do that. The way that we check the 2 functions are the same typically, if we know that both are functions from A to itself, is we just check that these 2 functions do exactly the same thing to every element of A. So that's what we'll do here. We will let x be in A, and we'll just keep track of what each of these functions does to x. So this is equal to epsilon of alpha of x, just by definition of composition. And then, well, what is epsilon of alpha of x? Epsilon of alpha of x, well, epsilon is a function which takes every element or every input to itself, which means the result of this should just be alpha of x. So that means that I've at least established, since x in A was arbitrary, I know that epsilon compose alpha equals alpha. What about the other composition? I know that alpha compose epsilon of x is equal to alpha of epsilon of x. Now this time I can use the fact that epsilon of x is just x. So I get alpha of x back. So this shows us that epsilon compose alpha is alpha because those do the same thing to every x. And alpha compose epsilon is equal to alpha because those two functions do the same thing to x every single time. So therefore, epsilon, this identity function, is in fact a group identity. Under composition. All right, so what's left? So we've shown that we have closure. Our operation is associative. And what else? We've shown that we have an identity element now. That's awesome. Okay, so we have that. Check. So now we just need to show that we have inverses. Each bijection has an inverse, which is also a bijection. Okay, probably not going to do this in full detail just because the proof would take me another 10 minutes, and I want to keep this video nice and tight here. But let's at least get started. Okay, so suppose alpha belongs to S sub A. That is, alpha is a bijection from A to A. Okay, I'm at least going to try and define what would be the inverse of this alpha. So let's define a new function, which I'll call beta for now, and then later on it'll turn out to be alpha inverse, and we could just call it that. From A to A as follows. I'm going to do this using the ordered pair idea of function to do the definition. So we're going to say that for x and y in A, we're going to say that x comma y belongs to beta if and only if y comma x belongs to alpha. So in other words, beta of x equals y if and only if alpha of y equals x. That'll be our definition of beta. All right. Now, when we do this, we actually, before we even start showing that beta is a bijection, we need to show that beta is a function. That it's a well-defined function, meaning that it actually does something to each element of A. Or to put it more in terms of the ordered pair definition of function, we need to show that for every x in A, that x can actually go in the input spot of an ordered pair. So in other words, we need to show that this part of the ordered pair can be any element of A. Otherwise, we have some elements of A that can't be inputs for this function, which is a problem if we're going to say this is a bijection from A to A. So why is that true? So why does every x in A appear as an input of B? Well, the reason is because we know every x in A appears in the second coordinate of this function. And the reason for that is because alpha is on 2. So every x in A gets hit as an output of this function. So this is because alpha is on 2. And then the other thing we need to show is, why does every x in A appear only once as an input? That is, no input corresponds to two different values of y. To two different in beta. Okay, so why does no x correspond to two different values of y? And the reason is no x here corresponds to two different values of y here, and that's because the function alpha is 1 to 1. If alpha failed to be 1 to 1, then I could have a couple of different inputs here that map to the same output, which means over here I'd have one input corresponding to several different outputs, which would threaten beta being a function. So the reason this is true is because alpha is not onto 1 to 1, because alpha is 1 to 1. So beta is a function. And I'll just say briefly why beta also will have to be a bijection. That's what will put beta in S sub A. So what would make beta 1 to 1, first of all? It would mean that we can't have multiple x's corresponding to the same y. We can't have multiple different values of x corresponding to the same y. Well, if that did happen, then what would happen over here? Because remember, these two functions are intimately connected. Well, that would mean that I have one y over here corresponding to multiple x's. that would mean that alpha is not even a function. If alpha is a function, then every y has to map to only one x, which means every y here has to correspond to only one x over here. So that's why beta is 1 to 1. And then why does beta have to be onto? Well, for beta to be onto would mean that every y corresponds to some x over here. That is, for every y there is some x which corresponds. Well, for every y over here, there is some x which corresponds, again, just because alpha is a function, and its domain is all of A. So for every y in A, there has to be some x corresponding, which means for every y here, there has to be some corresponding input. So that's why beta is onto. So I'm just going to write here that, in fact, it's a bijection. It's possible to write that argument more carefully. I just didn't want to make this video 10 minutes longer. Okay, so in other words, if alpha belongs to S of A, then beta, this function we defined, also is an element of S of A. But one thing I didn't show is that beta actually acts as a group theoretic inverse. So let's just do that real quick. So we need to check that, well, what do we need to check in order for beta to be an inverse of alpha? That would mean that composing the two gives us the identity. And who's our identity? It's this guy, epsilon. All right, so we need to check that beta compose alpha is epsilon, and alpha compose beta is epsilon. So let's do that real quick. Again, we're going to do it by showing that these two functions right here do the same thing to each element of A. So what is, let's let x belong to A. Then what does beta compose alpha of x? Well, that's beta of alpha of x. And then I don't know exactly what alpha of x is, but I could call it something. I could call it y. All right, so then that means that x comma y does belong to alpha. But then that also means, by our definition of beta, y comma x belongs to the function beta, which means that beta of y is equal to x. And that's the same thing as epsilon of x. So that means that beta compose alpha does the same thing that the identity does. So that means that we have checked these are the same function. And then what about alpha compose beta? Well, what is alpha of beta of x? Well, that's equal to alpha of beta of x. And then this time, I probably better not say beta of x equals y, because I've already defined y over here, and it wasn't defined exactly that way. So let's say that beta of x equals z. Just define a new symbol for that. Well, then that means that xz belongs to beta. And so by our definition of how beta and alpha relate, that means z comma x belongs to alpha. So what do we know? So we know that alpha of z is going to be the same thing here. And then, well, that means that alpha of z equals x. So I'm right back on x, which is the same as epsilon of x. So this composition also checks out. So therefore, beta is an inverse of alpha. And most importantly, we've shown that alpha has an inverse, which is also a bijection, also belongs to S sub A. That deserves an exclamation point, not a factorial. So anyway, there we have it. We have all four parts of the proof that this S sub A is always a group. It's always a group. But in this course, we're not going to use just any set A. We're going to focus mostly on finite sets. So usually in this course, A will be a finite set. Namely, the set of numbers from 1 up to n. So set of n elements. And when it is, we will just call the set not S sub A, not S sub the set of 1 to n. We'll just call it S sub n. So for example, S sub 5 will be the set of bijections of the set 1, 2, 3, 4, 5 under function composition. And we're going to have a lot of fun talking about how we analyze those groups in the next video. Yay!